Okay, well, we'll get going here today. Welcome to Physics 2820, Lecture 11. Today I want to talk about Taylor series, and with two applications. One is to integration again, because we began to talk about integration a week ago. And then if we get to it today, a little bit on how Taylor series will apply to solving ordinary differential equations. So just to review for where we were last time, we have discussed two of the methods of solving for integrating some equation, right? And the two methods we talked about were a rectangular rule and a trapezoid rule. The idea being the area under a curve can be approximated by the sum of a bunch of rectangles or the sum of a bunch of trapezoids, and each one of those would give you an approximation for the area under the curve. So just before we continue on here, I want to make sure these ideas are clear. So I've got a little exercise that I'd like to sort of do as a class. So the idea here is I'd like you to be doing this along with me, just to make sure all these ideas make sense. Let's try and figure this kind of stuff out. Okay, so the first thing here is what we're going to do is we're going to take a specific function, namely this guy, and we're going to integrate that. We're going to integrate it with pen and paper, and then we're going to integrate it with the trapezoid rule, the rectangular rule, and compare the two. So the first step in giving an equation is we want to be able to define that equation so we can evaluate it. So what I want you to do is write some code, or try and write some code, that evaluates that expression all the way through. As always, remember to start that first cell. And so a function that would do this would be something like, and then you fill in the blanks. What I'm going to encourage you to do is try to sort of do it just slightly before I do it. So you go, oh, okay, that's what I would have done, but fair enough. So how would this work? You have to evaluate that number and return the value. So this is a function which, given an x, calculates the sine of x and x cubed, because that's what we're asked to do. Let's plot that function between -10 and 10 to get a sense of what the shape of that function happens to be. So in terms of plotting, if you're given a function, the way of making any kind of plot is to define a range of x values and then evaluate that function for every one of those x values, and then plot the x values versus the y values. So what I mean by that is we would say something like, define an array using a range that starts at -10, goes up to +10, and then skips every 0.1. Once you have that array, you can actually use your function you just defined to evaluate at every point at x, and then make a plot of x versus y. So there we go. Hopefully that's what you're seeing. This is what the shape of this particular function happens to be. It's very flat near 0, and it goes up fairly large and goes down fairly large. That's the function sine of x, x cubed, all the way through. When you're making plots, it's always helpful to do a little bit of making them look pretty. So the x label would be x, and the y label would be y, obviously. So that helps a little bit. And to get rid of this thing right here, what we can do is we can end that cell with a plit.show. And so we get a function curve. That's what this function is. Okay, so what I want to do is I want to take this function, and I want to calculate an exact integral. I want to actually figure out, using pen and paper, what that derivative happens to be. So let me do it this way. Now, I think everybody who's in the room is also on Zoom, or most of you are. So how about I have you try and do this, and this would involve a scrap piece of paper or your best latex skills or whatever, using calculus. Figure out what the integral is. That is, what I mean is figure out int 0,5 sine of x plus x cubed dx. There. Evaluate that for me. And then, just to make sure we're all got the same answer, give me a numerical answer in the chat, and we'll know they're all on the same page. And just as a reminder, you don't need a calculator to do this. Remember that you can always evaluate these things directly. You can use Python like a calculator. And so I'll just wait here for somebody's numerical answer to throw up into the chat. It tells me that you're on the same page. And if there are questions and this isn't making sense, now's a great time to ask a question or ask Kyle for help or myself for help. Just looking for someone to do this integral. And if this is something that we're having a hard time doing, let's talk about it right now, because I'm assuming this is well within everybody's calculus skills. Okay, I got an answer. I got 154. Do you want to be more precise than that? Like 154 dot, like give me 5 or 6 decimal places? Okay. Does anybody else get that answer? Does anyone need help figuring out where that answer came from? I'm looking for confirmation from anybody else that they got the same answer or they got a different answer. Okay, so someone got 31.966. Okay, so we're not in agreement here. So let's take a step back and figure out what this might be. To do an integral, as you know, what you need to do is come up with an antiderivative. That is, you've got to integrate sine of x plus x to the power of 4. Now I'm using LaTeX here just to write it out, but you can do this on pen and paper. You need to evaluate what an antiderivative of this would actually look like. And of course, the rules are the antiderivative of sine of x is a function that when you differentiate it, you get back sine of x. It's the derivative of cosine of x, of minus cosine of x, is the antiderivative of sine of x. And it's the derivative, oh, well, not 3. It's the derivative of 1/4 x to the power 4. There, math notation. The derivative of this thing on the right gives you the thing on the left, right? Derivative of cos is minus sine. The minus sign makes it a sine. Derivative of x to the 4th. Well, the 4th comes down, reduce the power. So that's an antiderivative. And of course, what that means is what we need to do is we need to evaluate this function at the upper and lower limits. We need to evaluate this function at 5 and at 5 to the power of 4, right? That's evaluating the function at the upper limit. And then we've got to evaluate that same function at 0. So I get 156.966, which is not what anybody has got so far. Oh, that's what Sarah got. Perfect. Okay, so at least one person agrees with me. But you see, it is sort of tricky to be able to get this correct, right? But this is doing just normal math. Added and subtracting. Okay, right, because when you're doing integrals, it's the difference between the antiderivative at the first point and the last point. This is fundamental theorem of calculus. The purpose in doing this is to give us an exact answer we're going to check to. Now, the thing is, we're learning numerical methods of integrating because often there are functions you can't integrate. And even on this one that looks relatively simple, it turns out it's actually tricky to get the correct answer. So let's try some numerical methods, okay? The idea is to use a rectangular rule to approximate it. Now, in the copy of the lecture you have, right at the top here, there's some math. If you want to, double-click on that region and just take that bunch of LaTeX stuff, copy it, and then go down to this question where I said evaluate numerically integral using rectangular rule, and you could just edit that and paste that in. It's a nice way of seeing the formula that you're about to type out. You don't have to. You could always scroll up and down a bunch of times, but I think it's easier to have that right there in front of you. We want to evaluate this algorithm. So there's a couple things. A and B. Well, the A in this problem is 0. The B in this problem is 5. And I want to do this with 10 rectangles. So we know that part of the code. If we're going to evaluate it, the idea is to take the interval from A to B and split it up into 10 pieces. So it would make sense to write something like B minus A all divided by n. Okay, so far that's a program that will compute some of the things. If we're going to do a rectangular rule, the idea is we have to implement this thing on the right as a piece of code. Well, how do we do that? Well, it's a sum, and we're going to start the sum equaling to 0, and we're going to do a loop, and we're going to say for I in range of n. Now what this is doing is letting I take on every value up to, but not including n. It takes on the value of I equals 0, I equals 1, I equals 2, all the way up to a number less than 1, up to I equals 9. Exactly what we want. To compute the sum, we need to evaluate the function at this particular point. And that, of course, would just be the function at this particular point, where that particular point is equal to that. So this is taken straight from the definition of the algorithm. The idea is x is all of the values. Xi is a particular value between a and b. And the first value is a, the second value is a plus dx, the third value is a plus 2 times dx. We're evaluating the function at each point. And then what we can do is we can just add it up by taking the sum of fi and multiplying by dx. And then finally, we can print a little print statement. Okay. So that's what I get as a numerical answer to this problem all the way through. Now, it's going to have some error. That's not too surprising, and it's going to typically be an underestimate of it. So if you didn't have an exact formula, the rectangular rule would suggest the answer is 127.50. Now let's do this again by writing a piece of code, and I'm going to get you to do this. Can you write a piece of code that evaluates the integral, that is this thing right here, using the trapezoid rule? Again, what might be useful is for you to scroll up to the top, find this bit of mathematical notation, double-click on the cell so you can edit it, highlight that bit, copy it, Control C or Apple C or whatever kind of computer you happen to be using. Scroll back down to evaluate the integral with the trapezoid rule, and paste that in right there so you can see what you're coding right beside what you're doing it. And I want you to try and write a program very similar to this that evaluates this integral using the trapezoid rule. And again, what we'll do is once you have a number, whatever you come up with, post that in the chat, and then we'll talk about a solution. Kyle, could you give me some feedback on how hard or easy this task is going? Okay, we got an answer, 158.5138. That's one answer from Andrew. let me show you what I would do and see if I get the same answer. So if it was me coding this up, I would start by taking the code from the rectangular rule, just copying and pasting it because it's going to be pretty close to that. Test it to make sure I get the same run. The detail now is the sum doesn't start off at 0. It starts off by evaluating f at A and f at B. So in terms of what x0 and xn are, they are the points all the way through. If you want, you could sort of think about this as being x0 is the same as, well, I'll do it this way so it's really clear what it is. x0 is equal to a plus 0 times dx. Now, that's just the same as a. xn is equal to a plus n times dx, right? That's the general pattern for any point. But because of how we define dx, this first one is just the same idea as a, and this second one is just the same idea as b. But what we do is we evaluate the function, the first point and the last point. And then we want to divide each one of those things by 2. And that codes up the first part of the sum. Now what we do is evaluate this function when I goes from 1 to n minus 1. So the only difference is we want to start at the point 1 all the way through and add up all the values of fi all the way through. Finally, we're going to take that sum and multiply it by dx, like you see out here, to get the final result. But let me see if I get the same thing as Andrew does. I get 1585138515555, right? So you can copy and paste that. So I agree with Andrew. So there's the idea of writing up this piece of code. Okay, next part of this little exercise, I'll stop there. Are there any comments or questions about writing that piece of code? Okay, so what we have here is 3 different methods of evaluating an integral. Something that we're going to call the exact number, 156.96, a rectangular rule approximation, and a trapezoid rule approximation. So if I say, comment briefly on your answer, all we're really looking at is some statement like, for the same number of n, the trapezoid rule gives a much closer result than the rectangular rule. And you don't need to make the n look fancy, it's just how I tend to type things out, right? Why would that be true? We know that the trapezoid method is more exact, has less error than it all the way through. Now we can be more specific about this. We can comment on what the actual error is. So rather than just looking at the numbers, 156, 127, and 158, we can talk about the absolute relative error. And what that means is the absolute value of the relative error of the two things. Mathematically, that's just the numerical solution minus the exact solution divided by the exact solution. So if I want to talk about the error, what I want to do is I want to have the numerical solution minus the exact solution. So let's do it like this. Let's calculate the error in the rectangular result is equal to the absolute value of the rectangular result minus the exact value, all divided by the exact value, right? So that would work. The only difference here is I need to know what the rectangular value is. So I'm going to go back up to my code up here. And just before I'm done this piece of program, I'm going to save that variable so I could use it again later. Likewise, For the trapezoid rule, I'm going to create a new variable called trap so I can use that variable later. Then this piece of code will let me calculate the error in the trapezoid and in the rectangular method. And typically what's nice to do is have some little print statement to make this work out. There we go. Okay, so as a relative error, we have an 18% error in the rectangular method and basically a 1% error in the trapezoid method. So that's a more quantitative way of to start describing this. Let's kick it up a notch. Let's do this again, except for let's calculate when we've got 100 rectangles or 100 trapezoids. Well, as soon as doing it again becomes a thing, rather than going back and copying and pasting this code, it makes sense to start building some functions. So what I'm going to do is I'm going to go back up to my rectangular rule and recognize what I have here is basically a function. It's a function compute rectangular of n. So n is the number of rectangles. And what I want to do is turn this whole thing into a function. If you highlight all of the characters and then hold down the control key and the right curly brace, it'll indent them all at once. And if you're like, how did he just do that? Oh, sorry, control then the square brace. That key will automatically indent a bunch of code. So what I can do is I can turn this into a function that for any value of n, it just goes and calculates the rectangular rule. So now we can say compute rec of 10, or compute not rec, compute rec, 1, 2, 3. Compute rec of 10 will give me this value called rectangular. And I get the same value, it doesn't change. Likewise, I could turn my trapezoid function into a function. I'm going to change out that, and I will compute the trapezoid value of n. I can highlight all of this stuff right here. Control right square bracket to indent it. And then return this back as the result of this function. So now trapezoid equals compute trap of 10. And let's print out trap. And confirm nothing's changed. Once you bring in functions like that, it's much easier to answer questions like redo the same thing as in 7. So there's a bit of code there, but what I've basically done is I've translated these things into functions. And this is a common practice. You have some little bit of code that works. Once you have it working, we can start building it up into functions all the way through. Okay, so whether or not that piece of code or that piece of code, please let me know if you need me to pause on here so you have a chance to get this, but basically we're just indenting it and writing the code up. Okay, so now we'll get to this part right here. Redo as in 7, but do it for 100 rectangles. So what would that mean? We calculate the value of the trap, or sorry, of the rectangular one. 100. We calculate the value of the trapezoid. 100. And then this code down up here, just by copying and pasting it, would be exactly the same. So let's take a look at what we get. There we go. So well, that's sort of suspicious. That didn't seem changed for the trapezoid. Didn't look like it changed at all for the rectangular rule. So that suggests to me that I probably have a mistake somewhere in my code. So let me leave it to you for a moment. This is suspicious to me because the number didn't change at all. How about you convert your rectangular function and see if you can find my mistake? Why am I getting no change in the error of the rectangular rule, but my trapezoid rule got a lot better, the error reduced? There must be a mistake somewhere in my code. So how about you try and write your own versions of compute trap, and tell me where my mistake is. I do see my mistake, but I'll let you figure it out. Exactly, Cassandra. My mistake is that when I was copying and pasting, I left this line in, even though n should have been passed in. So no matter what I pass in, n was always being overwritten. So let's get rid of that line. Test the code again. It doesn't change because n is equal to 10. But if I calculate the errors, there we go. So the rectangular rule with 100 rectangles, the error goes down to 2%, which is better than 19%. The trapezoid rule went down from an error. Okay, hold on, let me just run these cells in order. Okay. The trapezoid rule went down from an error of 1% down to an error of 9.8 times 10 to the minus 5. So a very, very small number. So the takeaway of this is these two methods have different error behaviors. That is, depending on how many rectangles or trapezoids you use, you get a better performance in terms of how the error shrinks all the way through. What I want to do is I want to walk through making a plot of how the error depends on these values 100 or 10 or whatever. So what should be clear now is error gets reduced significantly by reducing the number of elements, and that the trapezoid rule is always more accurate than the rectangular rule. So let's write some code that loops through a number of different values of h and makes a plot. Now, I don't really want to do h equals 1, 2, 3, 4, 5, 6, 7, 8. That's too fine. What I'd really like to do is have h increase by large steps all the way through. So here's a way of creating a loop where the steps are not spaced linearly. So first of all, if I have some array, I could use a range that goes from 1 to 11 all the way through, right? So this is just, wrong indent. So this is just the function 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's an array that starts at 1 and goes up to but not including it. Rather than having to worry about the steps, what I could do is I could take that array and I could multiply it by something, and I get a new array that increases by steps of 2. What I want to do is I want to create an array that looks like this. 2, 4, 8, 16, 32, 64. An array that's sort of not linear all the way through. What's a way that I could take this starting array, 1 through 10, and come up with an array that looks like this? And I'll let you try a couple of approaches and see if you can come up with something. It's a one-liner. And the idea here is what we're doing is we're taking 2 to the power of that array. So this is a nice way of generating a sequence like this. So what we could do is we could make a graph at how the error, depending on how many rectangles we use, changes. So every time we're doing this, we're doubling the number of rectangles. Let's make a loop or a program that shows you how the error changes with these values. What I want to do is I want to create a 2-column matrix with the first column containing the number of elements and the second column containing the error. Now, I don't have to do it this way. I'm going to change the question because I can change the question. Let's create 2 arrays. One with one containing the number of elements used, and the second array the relative error. You could do this any which way you like. The point is, can you come up with 2 arrays so that one has the value of n elements you used, and the second one has the relative error? This guy right here is already the right answer. So I can right away say num elements is equal to 2 to the power of a. What I want is another array that has all those values in it. And the question is, what kind of code could we write to figure out what the error would be all the way through? Using rectangular rule, that sort of wasn't clear. Using rectangular rule. Okay. So there's 2 ways of doing this. You can do this with a loop or without a loop, but I'll take either one. And then once you've done that, once you have that array, we should be able to make a plot of the number of elements against this error and take a look at how the number of rectangles compares to the error. Now that won't work because I don't yet know what this is. So I want you to try and figure out a way, a method, some code to figure out an array of all of those values. And if you're confused, it doesn't have to be an array. A list would be just fine as well. So hopefully what you're thinking is something like, I'll need a loop where I want to pick off every one of these values in order. For each one of them, I'm going to calculate the rectangular rule using that number. For every one of them, I want to calculate the error. We've already figured out some code to calculate the error. And then what I can do is I can take this list, and one of the methods is just to append that to it all the way through. That's one solution. There are others. And the idea is we can get a graph. Whoa, that is not what I was expecting at all. That's very funky. Excuse me for a second. That's my array. That looks just fine. Whoa, that's cool. That's a lot more complex than I was expecting. What does one of these error recs look like? That's not right. What does one of these recs look like? That's not right. So this code is returning an entire sequence. What's n? 1024. So there's something that I've done incorrectly. Maybe your code works a bit better. Let me just go up and take a look here. Sum is equal to 0. So if I put in 1024, I get a number. Everybody's happy. Start with a number, get a number out. Compute rec. If I go down to here, and sometimes you need to debug things like this. Let's print out what that is. Let's print out what that is. And let's print out what that is. There are other ways of debugging, but this will work for our purposes. Int object is not iterable. Int object is not iterable. What it's complaining about is this thing. There. Oh, well, wait a second. A, for some reason, is no longer the right thing. Somehow, and I'm not sure how. Sorry, that took me a moment. I have written some code which is poor because A, way up at the top, I've defined as equal to the starting value. I am also using A for a different purpose. So just to be clear, this happens. Good choice of variable names. A and B, wonderful variable names all the way through. If you make A equal to something else, well, then it's going to use that something else. So down here, let's give this a different letter. I don't know. L. I like the letter L. L is fancy. That's fine. That's fine. That does help it. So now L is that array to the power of this. Now my program is working correctly. 2, 4, 8, 16, and it's calculating the error all the way through, getting smaller and smaller. Now that I have my program working, it's safe to either comment out or get rid of those things and delete these cells. And now we can plot. There we go. The error as a function of the number of rectangles. Right? So this is a nice way of doing it all the way through, and that's an example of how to debug. Now, how about you do the same thing? Can you write some code to make a graph so the error is plotted against the number of rectangles. So hopefully what makes sense is basically the same code, except for now we're going to calculate the trapezoid every time. And so we're going to get a slightly different curve. And the point is, this drops down very small, very, very quickly. If I want to compare these two graphs together, what I really want to do is I want to plot the number of elements against this thing. So let's do the following. Let's make this delta rectangle, delta rectangle, delta rectangle. So the error for the rectangles. And let's make this variable delta trap, and delta trap, the error for the trapezoids. And then what I can do is on the same plot, I can do the trapezoids and the rectangle. But of course, as soon as you've got a graph like this, it's difficult to see which one is which. So labels are helpful. And we can see that the trapezoid rule decreases a lot more quickly. There's something else about this graph, and that's the fact that the error is getting really, really small numbers. Rather than plotting it on this scale, what I could do is I could plot this on a log scale. And if I do that, we can see the behavior, how the error decreases with the number of elements. The slope of this line gives you the order of the method. This is decreasing with a slope of 1, so it's an order 1 method. This is decreasing with a slope of -2, so it's an order 2 method all the way through. And what we mean is the error, as a function of the number of elements, decreases all the way through. Okay, so I wanted to go through that process because it illustrated how you begin to work with some of these algorithms, how you can do some debugging, and how you can do some plotting to understand what you're doing. And you do want to make your plots look as good as you can fairly easily. You can change whether or not they're being plotted on a log-log scale or not. You can add in symbols. You can add in labels and legends. And these are all very standard, quick things to be able to do. Before I move away from this exercise, are there any questions about things we'd like to talk about? Either about the code or why we're getting the results we get. Why did I use log twice in the plot? Oh, well, because plit log isn't a kind of plot. There is a plot called semi-log x. There's a function called semi-log y, which makes a logarithmic scale on the x graph, x-axis, or on the y-axis. If you want it logarithmic on the x-axis and the y-axis, that's what log does. So I didn't use log twice. Log is the name of a function with log scaling on both the x and y axis. Basically, all that it's doing is it's doing a normal plot and then setting the scaling so the x-axis and the y-axis are both log scale. Any other comments about how to do these kind of plots or make these kind of things? And the point is, we started from an algorithm. So using this one bit of algorithm, we are able to start with any function and explore how well the method works. That is the rectangular rule or the trapezoid rule. And this is showing you the slope of this line. If you think about the slope of this line, it goes from 1 to -3. It goes from 1 to the 3. The slope on this thing, in log, the slope is -1. The slope on this thing, from 0 to -6, is -2. This means, because it's on a log plot, the error is decreasing quadratically with the number of rectangles. Okay, so there's some code. Let's do some math for the remainder of this lecture. This is a sit back, relax, and stare at some math. Hopefully some of this is familiar to you. Remember back to, and I'm assuming we cover this in first year calculus, but if we don't, I will tell you that there's this thing called a Taylor series. And the idea of a Taylor series is you can rewrite any smooth function as the sum that looks like a power series. A power series in the sense that it's a constant times x, x squared, x cubed, all the way through. And the specific choices we make for these coefficients to give you this form of the power series is chosen so that when you differentiate this polynomial, and remember, you always can differentiate a polynomial. F of a is just a number. Little typo. F prime of a is just a number. F double prime of a, for a is being a constant, is just a number. When you differentiate these things, 2 comes downstairs, cancels with the 2, and you're left with something you can evaluate. So if you evaluate this thing at x equals a, what you're going to be left with is the derivative f prime of a, or f of a. If you differentiate this thing, then you'll be left with the derivative of f prime when x is equal to a is equal to f prime of a. So this polynomial is exact for every derivative. It's made up of a series, so in practice it goes on forever, but we could talk about any term in this series, either the first term, or the first 2 terms, or the first 3 terms, as being a polynomial approximation of the function. When it's just a single number, the function is just a constant. T0 is a polynomial function that's approximated by a constant. T1, this term plus this term, is the straight line approximation to a function. And this term plus this term plus this term is the best parabola that approximates that function. Again, I seem to have little numbers that I've missed. Okay, so that's what a Taylor series is, and you can learn about Taylor's theorem and rules about that in calculus. What this means is I can given a function like f of x equals sine of x, evaluate its derivatives at 0. Derivative of sine is 0. The derivative of sine is cos. Evaluating cos at 0 is equal to 1. The derivative of cos is minus sine. Evaluating that at 0 gives you a 0. Derivative of minus sine is minus cos. Evaluating that at 0 gives you a minus 1. These values, 0, 1, 0, minus 1, these are the coefficients in this series. 0, 1, 0, minus 1. The Taylor series for sine of x around x equals 0 is x minus x cubed. This is the cubic approximation to a sine of x. You could keep on going. You could get next to the 5th term and next to the 7th term all the way through. This particular kind of Taylor series is called a Maclaurin series because we're doing the expansion around x equals 0. But the point is, and this is something that comes from Taylor's theorem, the difference between this exact value on the left and this approximation value on the right is some term which is proportional to x to the fifth. One way of writing that is to say sine of x is equal to x minus x cubed divided by 6 plus stuff, where stuff, the leading order of stuff, is some power of x to the fifth, and then terms that are smaller than that. When x is small, think of a number less than 1, and x to the 5 is really small, x to the 7 is very, very small, and x to the 9 is incredibly small. What that looks like graphically is the following. I've just coded up these three functions, and we can see a number of plots. The line in blue is the original function. That's sine of x. T1 of x is the linear approximation, a line going through the point x equals 0 that has the same slope and same intercept as the sine function. And you can see that if x is small, it actually is approximating sine fairly well. If we went up to the third order, this green line is the best cubic, that is something with x's and x cubes that approximates a sine function. It works a little bit further for a little bit longer range than T1 of x. If we wanted the best quintic, that is this curve right here, this thing in red, it's the best function that includes up to x to the fifth terms that approximates the sine function. Near 0, this red function does a very good job of approximating sine. Now, away from x equals 0, it doesn't do so hot at all. But the idea of a Taylor series is it's a very good approximation near to where you're dealing with. This idea of Taylor series is this, and I apologize, I don't remember what's covered in Math 1001 or whatever the equivalent is in what you've done. Have you seen Taylor series before in a math course? It's covered in Math 2000, okay? Math 2000, and Cassandra's doing that right now. Has anybody not taken or is not taking Math 2000? Someone did Math 2000 last year. The point is, this is something one can look up, one can learn about. It's a theoretical tool allowing us to approximate functions. I've told you what it is. You've now learned what a Taylor series is. Oh, someone did Taylor series in high school. Fantastic. Good high school you went to. It's an approximation all the way through. Okay, using that idea that we can rewrite any smooth function as a power series, that is a sum of things, I could also write a Taylor series like the following. F of x plus h is equal to f of x plus f prime x times h plus f double prime x times h squared over 2. This is another way of writing the Taylor series where we're doing the expansion around the point x at a distance h away. Fundamentally, what we're doing here is we're letting the value a be an x so that we're evaluating this thing at x plus h minus a, but if a is equal to x, then that means that this number right here is h, represents how far away you are all the way through. To compare this back to the more general definition of a Taylor series, rather than talking about x minus a and x minus a here, replace this with an h, replace this with an x, and you get the same expansion, and replace this with an x plus h. That is to say, you can always approximate f of x plus h as either the function, if h is small, or the linear version of it, if h is small, or the quadratic version of it, or the cubic version of it. And this pattern keeps on going. If I take this Taylor series and I solve it for this term right here. So what you're going to imagine doing in your mind's eye is taking that function, bringing him leaving him by himself and bringing all these other terms over to the other side and then dividing by h. What you'd be left with is f of x plus h minus f of x divided by h. Okay, there's a typo there. I don't want typos to throw anyone off. I guess strictly speaking, that's going to be a minus sign, and that's going to be a minus sign, right? If you rearrange these things. But the point being, as an expression, this number right here, this series is something which is of the size h. If h is a small number, this number is a linear operator or something that depends upon h. It's of order h. All the other terms are smaller than it because if h is small, h squared is even smaller than h. So what we're getting here is the result that f prime of x can be written as f of x plus h minus f of x divided by h plus some term that looks like that. We call the first term the forward difference approximation for the first derivative, and we call the second term the error term. And what it says is the forward difference approximation, and this is what we talked about a week ago, is an approximation which has an error on the scale of h. It means if you did the log-log plot, you'd find the slope being -1. If we take this same Taylor series, but now write it in a different way, starting from f of x minus h. The idea being, do the expansion norm of x, but now take a step backwards. You get some plus signs and minus signs all the way through. When you go to solve again for f prime of x, what you're going to get is you're going to get f of x minus h divided by h. And again, there'll be an error term on the order of h. This expression is what we called the backwards difference approximation for the first derivative. So this expression here is an approximation for what the derivative is. It's a different approximation than the forward difference. It's going to be a different number, but it'll have the same error in the sense that as h gets smaller, the error between this value and the true derivative will decrease linearly with h. But here's the power of this Taylor series stuff. If you take these two ways of writing down Taylor series, f of x plus h and f of x minus h, you take these two series and you subtract them. So take this series minus this series. F of x minus f of x, those f of x are going to cancel. F prime of x minus f prime will become 2 times f prime of x. And there'll be a 2 times f cubed of x all the way through. I can solve this expansion again for f prime of x. So I'm solving this expression, and what I'll be left with is the f of x plus h minus f of x minus h on the top, divide by the 2h, and you'll be left with something which is of the order of h squared. This is yet another approximation of the first derivative. It's called the centered difference approximation of the first derivative, but it has a relative error of h squared. What that means is if you were to make a plot of the error in this approximation as a function of h, you will see the slope on a log-log plot being -2 all the way through. So this is a way of deriving different formulas for derivatives and estimating their error. And that's the power of this tool. We can take these two expressions, these two different definitions for the Taylor series, and not subtract them, but we can add them together. Imagine adding those two Taylor series together. And this is something that's good to sit back after the lecture and go through again. If I take those two derivatives and add them together, the f of x's add together, the f prime of x's cancel out, the f double primes add together, and this becomes the series. I could now solve that expression for f double prime of x and come up with an equation or an approximation for the second derivative. So this thing is the central difference approximation for the second derivative. And that is an order h squared approximation. Okay, so the Taylor series is the mathematical tool for coming up with these expressions and coming up with what their errors are. You don't have to do this. It's a theoretical tool. We can also discover these approximations or these errors by doing some simulations. So let's do specifics. Let's deal with a function like sine of x and evaluate that at pi over 4. So in code, we would say x equals pi over 4, and there isn't a pi symbol, but numpy.pi defines pi. I'm going to define a function called y equals sine of x, and I'm going to do this with this lambda notation. It's a mini function. You could rewrite this as a def f of x return np sine of x. And I'm going to evaluate this function for its 0th derivative. That is the constant function. Evaluate this at x and evaluate its first derivative. I'm coming up with the first derivative just by doing it by hand. And the point is, dealing with x equals pi over 4, its first derivative is 0.70710678. That's an exact answer. If we calculate the first difference approximation, we're calculating this thing on the right. In code, what that means is you're taking f of x plus h minus f of x, or y of x plus h minus y of x, and dividing by h. And so what we can do is we can figure out what the value is. 0.67 is that's the estimate or the approximation, and what the error is. Now, this error, this is an absolute value here. So we have an error of 3.7 times 0.04 all the way through. If I reduce h by a factor of 10 and run the same code, you'll see that the error has decreased by a factor of 10. So I've gone from an error of 0.036 to an error of 0.0035. The error has gone from 10 to the minus 2 to 10 to the minus 3. Reducing h by a factor of 10 has reduced the error by a factor of 10. That's what we mean by a linear dependence on h, order h. Now, there was another way of approximating the derivative, the center difference. The center difference was the idea that you could approximate a derivative not with this formula, but with this formula. Evaluate the function at a step to the right, a step to the left, and divide by 2h. So let's do the same thing. Let's set h being 0.1 and evaluate the center difference as x plus h minus x minus h divided by 2h, and take a look at what the error is. You're getting an estimate or an approximation of the derivative being 0.7059, which is an error in 1 part in 1,000. The error is 0.001. The point, though, that I want to make is when you reduce the size of h by a factor of 10, what happens to the error? You can see that when h goes from 0.1 to 0.01, the error, that is the difference between the exact value and the real value, goes from 0.001 to 0.00001. And when we start counting all these different zeros, sometimes using a logarithmic scale makes more sense. So I've gone from an error of 1 part in 1,000 to 1 part in 100,000. Decreasing h by a factor of 10 decreased the error by a factor of 10 squared, or by 100. This kind of error is due to the Taylor series approximation, and it's called truncation error all the way through. So we can explore this by looking at how these approximations change based on their values of h. Now, the thing is with any of these schemes is you can't just make h as small as you like. It's not enough to take a scheme like this, forward difference, and just make h very, very tiny. Because on a computer, you're only able to resolve floating point numbers with a fixed amount of precision. This other kind of error, that's called round-off error, has to do with that finite precision in a computer. Let me demonstrate this to you. Imagine I'm dealing with a forward difference. That is f of x plus h minus f of x, or y. And h is very, very small, okay, 10 to the minus 7. Well, I get a very small error, 10 to the minus 8th. Okay? Let's go and make h even smaller. So we're taking an even smaller step size. So h is going to increase by 1 part in 10 to the 9. Notice that the error has stayed the same. So even though we've shrunk h by a factor of 100, the error is actually not changing at all. Up to this point, as h was 0.1, 0.01, 0.001, the error is reducing by a factor of 10 every time we reduce h by a factor of 10. But once you get h small enough that the finite precision of the computer starts to interact with it, you stop getting any benefit. In fact, even if you go any smaller and you go to h equals 10 to the minus 11, your error starts to increase again all the way through. This kind of error behavior is not truncation error, but it's due to round-off errors. This is why we need more advanced methods to integrate things and solve things. Okay, looking at the clock, I see that it's 3:15. I just want to briefly finish off this unit on integration, and we'll leave the ODE stuff for next week. Using these ideas of power series expansion, we can derive a new way of integrating something. What we can do is talk about the integral of some function, and rather than approximating it with the trapezoid, we can approximate it 3 points of that integral with the best parabola that goes all the way through, connects those 3 points, and figure out the area under this curve. That scheme of looking at areas under parabolas is the basis of something called Simpson's rule for integration. Now, the details of the analysis of how this comes up is not overly important, and I encourage you to go back and look at this. But the idea is, say you have some function f of x, and I want to integrate it from -1 to 1. I'm going to approximate that integral, or that function, as some parabola. Sort of like a Taylor series, but in this case, it's a parabola that goes through the function. If I could write that in terms of an alpha times x squared plus beta times x times gamma, then the integral of this thing would be 2/3 of alpha plus 2 times gamma. That's just the integral of any parabola. I don't know, for a given function of f of x, what the parameters alpha, beta, and gamma should be, but I can solve for them. Evaluating f at -1, assuming that I can write the function as alpha times x squared plus beta plus x times gamma, it's sort of like a second-order Taylor series, means I can evaluate this function when x is equal to -1, evaluate it when x is equal to 0, and evaluate it when x is equal to 1. What this immediately tells us is the value of the function when at f equals 0, that must be the value of gamma in this system of equations. I can then go and solve for alpha all the way through by adding these two equations, eliminating the beta. What that means is to figure out the integral from -1 to 1 of any equation by approximating it as the parabola that goes through the points f of -1, f of 0, and f of 1, that can always be done as 2/3 times this quantity plus 2 times this quantity. This is an approximation, or the area under a parabola, that goes through 3 points. Given a function that I know at point -1, 0, and 1, the area under that integral is all the way through. If I take that code and I think about it now for a function that has this shape, that is a function with 1, 2, 3 points, 1, 2, 3 points, and 1, 2, 3 points, I can figure out the area under any triplet of these things as being the area under the parabola that goes through each set of points. Now, mathematically, that just means figure out the area of this thing, the area of this thing, and the area of this thing. And I can use the derivation I give above. I said I encourage you to go through this on your own time and figure out that this expression gives you what that should be. What this is really saying is you can write the area of something by evaluating the function at the beginning and the end of the interval, and then multiplying either by 4 or by 2, depending on if it's an even or odd point all the way through. In general, Simpson's rule is a scheme that says you can write any number of integrals, and now it's got to be one where you've got an odd number of points in total. If you sum it up like this will be a scheme with even better accuracy all the way through. Wikipedia has a nice little algorithm on what this looks like. Basically, these slopes, or these red lines, those are the different parabolas that are approximating each one. One of the things we could do, and I think we should do, is discover what the error is associated with Simpson's rule. So look forward to this on either the lab next week or an assignment question. I will get you to write some code that implements Simpson's rule and discovers what its error is. That is, how does the error decrease with h all the way through? Okay, so we're at whatever it is, 3:20. That's the end of the lecture. There's no lab today, though we will have a lab next week. And next week, I'll get started on applying this idea of Taylor series to ODEs, and we'll talk about Runge-Kutta methods. But I think that's a good spot to leave this lecture today. Any follow-up questions or anything we want to talk about right now? Okay, with that, I'll end this lecture.